All right, I'm hoping the third time's the charm here. Sorry, y'all. So we've got a weird circuit here. We've got a capacitor, plus, minus, with potential difference curly E, and we have an inductor, and there's a switch right here that's been closed, S, so that the current's going to flow this way, and then it's actually going to flow back the other way, back and forth. This is going to end up as an oscillator, which is super weird. Oscillator. And I'm going to prove that to you. So this has inductance L. This has capacitance C. And hang on, capacitance is equal to total charge over the EMF. So we're going to remember that. Let's see. So the energy stored in this thing is going to come from two sources. It's going to come from the magnetic, and it's going to come from the electrical. So we have an inductor that's storing potential energy. So this is magnetic in nature. We have a capacitor, which is storing energy. This is electric in nature. And the thing is, there's nowhere for the energy to go. So the thing that we need to remember is that du dt, the change in energy as a function of time, has to be zero. So if we write down an expression for potential energy, we know that its derivative has to be equal to zero, and that may actually lead us to show this thing as a simple harmonic oscillator. So let's write all that down. That would make so total energy is going to be for a capacitor, no, for an inductor, it's 1/2 L times I squared, and I is a variable in this case. That's why it's lowercase I, plus 1/2 Q squared. Ooh, here, wait, let's write it differently. Q squared over 2C. It's 1/2 Q squared over C, but Q is also a variable in this case. So what we need to do is differentiate this with respect to time. So if we differentiate that first expression with respect to time, we're going to end up with, let's see, 1/2 L times 2I, and then what do we get? di dt, right. I can do differentiation. And then the second expression is going to be q squared. Well, wait, we've got a 1/2 too. Let's not forget the 1/2. So we'll have this one, oops, we've got a 1/2, I guess 1 over 2c. Let's leave that there. 1 over 2c, and then times 2q dq dt. All right. So the deal, though, is so this entire thing is going to have to actually equal zero. Let's rewrite that. It's a big mess. So the 2's canceled. What's our final thing? We're going to end up with 0 equals. Remember, the derivative of this thing has to equal zero. That's the whole point. Zero is going to equal, let's see, L times I times di dt. We still have that in there. And then plus Q over C, yes, times dq dt. And the thing is, that's not a super helpful expression, right? But the thing is that dq dt is I, right? And di dt is the same as the second derivative of charge with respect to time. So we actually do have related differential equations. It's not obvious that we do. We got to kind of remind ourselves that the current is literally defined as dq dt. And if I'm taking the derivative of I, then that's the second derivative of, so this is kind of like velocity is derivative of position versus time, and acceleration is derivative of velocity. It's the same idea. So that means we can rewrite this expression as, let's see, that would make this 0 equals, if I have, this would end up as L times second derivative of charge with respect to time plus Q over C. Well, hang on, I'm skipping an intermediate step that may be a little bit needed there. If dq dt is I, let's write that. Let's not mess this up. L times I times di dt plus Q over C times I. So then look, we got both I's cancel out, and then we're left with L di dt plus Q over C, and the whole thing equals zero. Well, the deal is that we can, this expression that we have here can be rewritten. So if we write this as, let's divide everything by L. So we got 0 equals the second derivative of charge with respect to time, plus 1 over, that's L times C now, times Q. Y'all, this is in the form of a simple harmonic oscillator. If the, oh, that's the second derivative. If the second derivative of a function plus some constant times that function equals 0, then we can model it using cosines like we have before. So that means we can use Euler's method, like the same way, oh, wow, let's not erase that. The same way we did this for springs, Euler's method. We can model this. Q is then going to be, I guess we could think of that as the maximum Q times cosine of omega t, where this stuff right here is our omega squared.